right, we're ready to look at 8.6, the root and ratio test. That is, believe it or not, our last video of this semester. So far we've been answering all the true-false questions. Does it converge or not converge? And we have an abundance of tests. Well, this root and ratio test is the final test we're going to learn before your final and next week. So let's see what the root and ratio test is. Well, basically, it says if we look at the limit as n approaches infinity of the absolute value of a to the n plus 1 over a to the n. So we're talking about we have a infinite series of a to the n. And if we look at the limit as a to the n plus 1 is just adding 1 to the term. So if it says that the next term divided by the previous term, the absolute value of the limit as n approaches infinity. If that's less than 1, then we say it converges. If that value is greater than 1, or we say it diverges. And by the way, infinity would be greater than 1, so that's something to look for there. If it's equal to 1, it's inconclusive, and we can't use this test. We have to use another test. Well, that's the math gibberish. I think a lot of times it's easier just to see an example. So I want to talk about the summation as n goes from 0 to infinity of 2 to the n over n factorial. These are the kind of ones that come up a lot for the, and we're going to start with the ratio test. All right, so the theorem says if I can look at the limit as n approaches infinity of the absolute value of the next term, the n plus 1 term. So I'm going to put n plus 1 in for n. 2 to the n plus 1 over n plus 1 factorial. And if I can divide that by the original one, 2 to the n over n factorial. So, and then evaluate this. Now what this is saying then, if this is going to be less than 1, we can say it converges. If it's greater than 1, including infinity, we say it diverges. The only problem is if it equals 1, we've used the wrong test, and we've got to go back to one of the other tests that we have in our arsenal of tests. So this is why a couple weeks ago we did that practice on the bell work, because now first thing I need to do is simplify this. So we have the limit as n approaches infinity. Dividing by the fraction is the same as multiplying by the reciprocal. So this is 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n. Dividing by any fraction is the same as multiplying by reciprocal. You may recall from our bell work when we rewrote 2 to the n plus 1 as 2 to the n times 2. The same base, you would add the exponents. We're just going backwards there. So 2 to the n plus 1 is 2 to the n times 2 times n factorial, just going across. On bottom, I'm going to rewrite n plus 1 factorial as n plus 1 times n factorial. It just reduces down a lot. You remember doing that as well. N plus 1 times n factorial, and then times 2 to the n. Well, the 2 to the n's cancel out. The n factorials cancel out. And it leaves me with the limit as n approaches infinity of 2 on top over n plus 1 on bottom. And we know that that's heading to 0. 0 is a number less than 1. And our test said if it was less than 1, we can now say it converges. So we know that this one indeed converges. All right, let's look at another example of that. So I'm going to talk about example 2a. The summation as n goes from 0 to infinity of n squared times 2 to the n plus 1 over 3 to the n. Okay. Now I'm going to hopefully be able to skip a step here. Instead of writing it as dividing by the fraction, I'll multiply by the reciprocal initially. So the limit as n approaches infinity. First thing I want to do is add n plus 1. So everywhere I have an n, I'm going to put n plus 1. So all three of those n's have to be n plus 1. So instead of n squared, n plus 1 squared. To the, if this n is n plus 1, n plus 1 plus 1 is n plus 2. over 3 to the n plus 1. And then I divide by my original formula, and dividing by any fraction same as multiplying by the reciprocal. So this is same as multiplying by 3 over n times n squared over 2 to the n plus 1. Let's do some math magic and reduce this. So we have n plus 1 quantity squared, 2 to the n, 2 squared, just rewriting that one as 2 bases, times 3 to the n, all over 3 to the n times 3, rewriting that one with 2 bases, n squared, 2 to the n times 2, rewriting that one with 2 bases. All right, so now I have a 2 to the n top and bottom. I have a 3 to the n top and bottom. 2 squared divided by 2 is just simply 2. 4 divided by 2 is 2. So what do I have left? I'm looking at the limit as n approaches infinity of 2 times n plus 1 quantity squared over 3 times n squared. Now remember, for the purposes of limits as approaches infinity, I'm only looking at the leading term. Leading term here would be n squared times 2 would be 2n squared. Leading term on bottom is 3n squared. The exponents are the same top and bottom, so I just divide the coefficients. So this thing is heading to 2/3, which is a number less than 1. So based on my ratio test, I can conclude that the original function must have converged as well. All right, now let's look at another example. And this one, we're going to say from 1 to infinity, negative 1 to the n, square root of n over n plus 1. All right, setting this up as the ratio test. We are going to say, remember, it's the absolute value. So it's the limit as n approaches infinity of the absolute value. Now the absolute value takes that alternating part away, because it doesn't matter if it's negative or positive, it's always going to be negative. So what I can really just consider is what's going on with the a sub n thing. So I add 1 to this, n plus 1, over, if I add 1 to this n, it's actually n plus 2, and dividing by any fraction, same as multiplying by the reciprocal, n plus 1 over square root of n. So we're looking at the limit as n approaches infinity. Let's put these square roots together. Square root of n plus 1 over n times n plus 1 over n plus 2. Now, as this thing's getting very large, this one's heading to 1. As this is getting very large, this one's heading to 1. So this heading to 1 times 1, it's equal to 1. Inconclusive. Remember, less than 1 divergent, greater than 1, less than 1 convergent, greater than 1 divergent, equal to 1, inconclusive. So it didn't work. So we'd have to go to another test. Well, the easiest test would have been, obviously, alternating series. Because remember, with alternating series, this part just has to be heading to 0. And since the biggest power is on bottom, it is heading to 0. So this one would have been easier to prove that it does indeed converge by alternating series test. All right. The second part of this section is about the root test. And the root says if you have the summation as n goes from 1 to infinity of a sub n, that if you look at the nth root of a sub n and that limit as n approaches infinity, that if that is less than 1, guess what? It converges. If it's greater than 1, including infinity, then it diverges. And if it's equal to 1, it's inconclusive. So same set of rules. Now we're just looking at the nth power of a to the n. This happens a lot when you run into things that have the nth power top and bottom. Let's look at an example of what I'm talking about. So if I wanted to look at the summation as n goes from 1 to infinity of e to the 2n over n squared, or n to the n. Sorry. N to the n, not n squared. Well, that's this. I could write that as the summation as n goes from 1 to infinity of e over n e squared to the n. So I could write them both as raised to the n. And the reason I'd want to do that is the nth root test says if I take the nth root of that inside part, of the inside part, but of that, which is e squared over n to the n. And if that's less than 1, and the limit as n approaches infinity, if that is less than 1, then we say it's convergent, greater than 1 divergent, equal to 1 inconclusive. Well, the reason we did that is those cancel out. So it leaves me with the limit as n approaches infinity of e squared over n. E squared is just a number. So a number divided by n, as n gets very larger, this is equal to 0. It's less than 1, so we say it indeed converges. So that's the root test, handy for those kind of problems. The trick you're going to find is, now that you have all these, is trying to decide which test to use and when. All right, I'm going to back up and do another example in the book, just because it's interesting on the way it turned out. Example 2b. The summation as n goes from 1 to infinity of n to the n over n factorial. I said back up because this is actually, I'm going to do it by a ratio test, because they're not both raised to the n. Well, this is an interesting one because you can't even make any guesses, because we know that factorials are very large, and we know that n raised to the n is a very large number. So it's hard to even take a guess what's going to happen. So let's see if we can use the ratio test. The ratio test says take the limit as n approaches infinity of n plus 1 raised to n plus 1. Everywhere I had an n, I just put in n plus 1. All over n plus 1 factorial. Dividing by the original one, dividing by any fraction, same as multiplying by their reciprocal. So n factorial on top, n to the n. This is the limit as n approaches infinity of n plus 1 to the n times n plus 1. Just like I did to the 2 to the n plus 1 is 2 to the n times 2 is the same logic I used on that one. Over n plus 1 times n factorial. We've done that a couple of times, just rewriting that like that. Times n factorial over n to the n. Well, the n factorials cancel out, the n plus 1's cancel out, and that leaves me with the limit as n approaches infinity of n plus 1 to the n over n to the n. Now we're going to do some trickery, and I'm going to write both of those to the power of n. So I just rewrote, since they're both to the nth power, wrote it like that. I'm going to divide everything by n, so I get the limit as n approaches infinity of 1 plus 1 over n to the n. Now, if you notice, I put infinity in here. I get 1 plus 0 to n. So I basically have 1 to infinity. And you may recall that that's one of L'Hopital's indeterminate forms. So we could use L'Hopital's rule. But we already did this problem, if you remember in L'Hopital's section. And this is the shortcut, the trick. You may recognize that, you probably don't, as the definition of E. It's the limit as n approaches infinity to 1 plus 1 over n to the n. We proved that with L'Hopital's rule, so if you need to, go back and look at L'Hopital's rule. But we proved that that limit is actually E, and that's the definition of E. E is a number, 2.71, something like that. Clearly greater than 1. So with all that said, now I know that it's greater than 1, it's conclusive, it tells me it's divergent. All right, that's your last video. Good luck on your final.